Class, today we're going to be working with inequalities. So we can substitute values for variables in the inequality and prove that the statement remains true. We're going to be solving with addition and subtraction. So please start with the warm-up. I'm going to start with example 1. For each equation, or I should say inequality, decide whether the given number is or is not a solution. So let's just review our inequality signs real quick. Remember, this one means less than, or we have less than or equal to. And then we have greater than, or we have greater than or equal to. So if it points to the left, that's less than. So our first example here says x is less than 15. Is 10 a solution? So is 10 less than 15? I would say yes. X equals 10 is a solution to that inequality. In number 2 here it says x is greater than or equal to -5. So is 3 greater than or equal to -5? All positive numbers are greater than negative numbers, so yes, 3 is a solution to that inequality. Number 3 says, is x greater than 0? Is -5 greater than 0? Yes, it is a solution. And the last one says x less than or equal to 5, so is 5 less than or equal to 5? Since it is the equal to part, yes, 5 is a solution. So in this case, all of these are solutions. So the solutions are what are making the inequality true here. Example 2, tell if the given value is a solution to the inequality that is graphed on the number line. So if I look at my number line here, I have a closed circle at -2, and my shading is all of the values that are to the right of -2. So that means these x's are all the x's that are greater than or equal to, since it's a filled in circle, -2. So let's see if these are solutions. Is 11 greater than or equal to -2? Yes, 11 would be right here. This would be a solution. How about -2? Is -2 a solution? Since it is equal to, it's a filled in circle. So yes, it is a solution. It is included because of the equal to part. And then 25. Well, 25 is not on my graph, but you'll notice that this actually goes on infinitely. And so 25 is still bigger than -2, so 25 is a solution. So let's do some non-solutions. That would be anything that is to the left here, anything on this side. So x cannot equal -4. X could not equal -12, etc. So those are some examples of numbers that don't work. Let's practice this one more time. Let's look at my number line first here. I have an open circle at 12, and then the left side of the graph is shaded. So this would be this graph represents the inequality, all my x's that are less than 12. So not equal to 12 this time because it's an open circle, which means x equals 12 right here in the middle is not a solution. That's what the open circle indicates. -50 would be, ends at -18, but if you continue further, -50 would be way over here. So this one, -50 would be less than 12. So -50 is a solution. Same argument with -30. -30 would also be a solution. Yes. If I change that to +30, that would be over here, and that would not be a solution. So it has to be in that range of values. So all numbers less than 12 are solutions, except for 12. All right, graph x greater than -5 on the number line and name 2 other solutions. So x greater than -5, I'd have an open circle at -5, and then greater than -5 are all the values to the right. So -4, 0, 5. So name 2 other solutions. I could say x equals -4 is a solution. x equals 5 is a solution. You could give me x equals 100, anything bigger than negative 5. Since it is an open circle, x cannot equal negative 5 though. So you could pick anything that's shaded along this line as part of your solution set, but not the point negative 5 itself. All right, we're going to start looking at some algebra concepts here. So our typical inequality statement says like 4 is less than 17. Now look at the inequality here. It says x is less than y. It is read as x is less than y. No matter what values we substitute in for x, it always has to be less than y. So we'll fill in some values at work. For example, I could say negative 5 is less than positive 5. 0 is less than 4. 10 is less than 20. I want all my x values to be less than y. 15 is less than 16. Negative 20 is less than negative 10, etc. You can continue on. So that's a table of values that represent all sorts of possibilities for x is less than y. Now I want you to consider the same idea. 10 is less than 25. And I want to consider the statement 10 plus x is less than 25 plus x. So essentially we know that 10 is less than 25, and I want to know what happens if we add the same number to both sides. Would the statement still be true, or would it be false? So I started with the fact that 10 is less than 25. Then I want to add x to each side. In the first example, I'm going to add 5 to both sides. So 10 plus 5, is that still less than 25 plus 5? Well, 10 plus 5 is 15, and 25 plus 5 is 30. Is 15 less than 30? It is. Okay? So if I add a positive 5 to both sides of my inequality, it remains true. Let's try it with a negative. So I started with 10 is less than 25. If I add negative 2 to both sides, it'd be 10 plus negative 2. Is that less than 25 plus negative 2? 10 plus negative 2 is the same thing as 10 minus 2, so that's 8. 25 plus negative 2 would be the same thing as 25 minus 2 is 23. So is 8 less than 23? And I would say yes, it is. So adding a negative to both sides did not change the inequality. It stayed true. Let's try it with a fraction. 10 is less than 25. Is 10 plus 1/2 less than 25 plus 1/2? Well, 10 plus 1/2 would be 10.5, 10.5. And 25 plus 1/2 would be 25.5. And 10.5 is still less than 25.5. So this is still true. So you could add a fraction to both sides of an inequality, and the inequality stays true. So hopefully you've seen the pattern here. That's actually called the addition property of inequality. If you know that, you have two numbers and A is greater than B, then if you add the same number to both sides, that sum will still be, the inequality will still be true. Or like we did, A is less than B, then even if you add the same number to both sides, it will keep the inequality true. Now we use that addition property of inequalities. It's an important property because we use it to solve inequalities. Just like we did with solving equations, we're using our inverse operations. So to solve the inequality, we want to isolate the variable. We want to get the x variable by itself. So we're going to use our inverse operations. We have a plus 3 here. The inverse of adding 3 is to subtract 3. But we have two sides to this inequality. We have x plus 3, and then we have greater than 4. So we have the left side that says x plus 3, and we have the right side that has 4. So if I subtract 3 from the left, to keep the inequality the same, I would have to subtract 3 from the right side as well. I subtract 3 from the left because then I'm left with just x. 3 minus 3 is 0. That cancels. So then I have x is greater than 4 minus 3 is 1. Now I have my inequality and it's solved. X is greater than 1. So this inequality statement, x plus 3 greater than 4, has the solution x is greater than 1. Let's graph that on a number line. Let's see. When I graph this on a number line, I like to put my answer in the middle. So, and then I'm going to put a couple to the right. So 1, 2, 3, 4, couple to the left, like 0, then -1, -2, -3, for example. X is greater than 1 means I'm going to have an open circle at 1, and all my answers are going to be the values for x that are bigger than 1, so to the right. So this has multiple answers, and unlike the equation where x equals 1 was our solution, there are multiple solutions here, infinitely many. I could plug in 2 and I would get a true statement because 2 plus 3 is 5 and that is greater than 4. 3 is an answer because 3 plus 3 is 6 and that's greater than 4. So any of these x's to the right of 1 are solutions. The only one that wouldn't work here would be 1 because if you plugged in 1, 1 plus 3 is equal to 4, and 4 is not greater than 4. 4 is equal to 4. So that's why we have that open circle at 1. So those are your solutions. All right, let's try it again. We have a 5 plus y less than or equal to 7. Since I have a positive 5 here, and I'm trying to solve for y, I want to get the y by itself. So to get rid of a plus 5, I would have to take a minus 5 on both sides. So I do this to the left, I'm going to do it to the right, I'm going to do it to the left side of the equation as well. Because 5 minus 5 is 0, so this side I have y. And then we learned from the addition property, if I add the same number on both sides or subtract the same number on both sides, my inequality stays true. So the inequality stays less than or equal to, and 7 minus 5 is 2. So we get y less than 2 is our solutions. So I can graph that, put 2 in the middle, and then do like 2, 3, 4, 5, and then, oops, 2, 1, 0, -1, -2, -3 maybe. This time our solution set does include 2 because it's less than or equal to. So I would put a closed circle or fill that circle in at 2. And then all my answers are less than 2. So any number to the left of 2 would make this inequality true. For example, y equals 0 could be a solution. If I think about 5 plus y less than or equal to 7, the original, 0 is an answer because 5 plus 0 is 5, which is less than or equal to 7. 2 is an answer because 5 plus 2 is 7, and 7 is less than or equal to 7. It is equal to. So the equal to part includes that solution then. And any answer to the left, then -3, -100, -1.5 would be a possible solution. Okay, y is less than, or y minus 10 is less than 3. So here we have a negative or a minus 10. I want to get w by itself. So to get rid of the minus 10, I'm going to do the inverse operation. I'm going to add 10. But I'm going to, whatever I do to the left side of the equation, I have to do the same thing to the right. So I'm also going to add 10 over here. And then my property of inequalities, the addition property, said as long as I add the same number to both sides, the inequality will stay less than, it'll stay true. On the left, -10 plus 10 is 0, so I just get w left on that side, and 3 plus 10 is 13. So I get an answer that w is less than 13. On the number line, if 13, 14, 15, 16, maybe on the left, 12, 11, 10. It is not equal to 13 though, so it'd be an open circle and it would be all of the values to the left. Looks like I accidentally made this one into an equation, so I'm going to make it into an inequality, and I'm just going to make this a greater than or equal to 8. It's supposed to be an inequality. In this one, I want to get x by itself, which means I need to somehow get rid of the -4 on this side. It says -4 plus x is greater than or equal to 8. Well, a -4 is the same thing as subtracting 4. So the inverse of -4, -4, is a +4 or adding 4. So do that to both sides of the equation, because -4 plus 4 is 0. And then you're left with just x on that side. As long as you add the same number to both sides, the inequality stays true and it stays facing the same way. Then 8 plus 4 is 12. So we could use the same number line we have up here because 12 is very close to 13. So our answers are all our x values that are greater than or equal to 12. This time it does include 12, so we draw our circle at 12 and we color it in because 12 is part of our answer because it's equal to. And then all the values that are greater than or equal to 12 are to the right on the number line. And then we draw an arrow at the end here to indicate that even though I only graphed up to 16, this number line does continue infinitely in that right direction. Okay, that's all I got, folks. Make sure to do your 3.2a homework after watching this video.